Hello, my name is Jeremiah Gasson Smith, and I'm at the University of Texas at Dallas. So I do have a little footprint at the University of Texas Southwestern Medical Center. And today I am going to bring a discussion to you about some work we're doing in controlling vaccine delivery and in a way to enhance antigen presentation using specifically coordination polymers. So the session description is essentially this. I'm going to provide a background on vaccine technology, well, specifically our vaccine technology, and highlight some of the deficiencies with existing vaccine technologies, specifically in the context of whole cell vaccines. And hopefully at the end of my talk, you will um, have a bit of a better understanding of some of the shortcomings of whole cell vaccines and some of the ways that we are working to improve them. All right, and since I am not physically there, I figured I'd show you a picture of me, actually me. So this is what I look like today in 2020. As you can see, the pandemic has not been well, I grew a beard. I have you. Everybody has these pictures that they put up, and they're all like 7 years old, and I look much better in that one. But I figured I would just kind of be a bit more realistic and show you, what contemporary me looks like sitting on the couch. I did get a PhD specifically in physical organic chemistry and materials and nanoscience as a postdoc in the lab of Sir Fraser Stoddart. And now I'm an associate professor of chemistry with a secondary appointment in bioengineering at UT Dallas and UT Southwestern. Um, and you can email me or you can follow my shenanigans on the internet through Twitter if you would like. Okay, so proteins, right? That's essentially what most vaccines are. There are certainly some toxoid vaccines and stuff like that. But vaccine technology still largely relies on the proteinaceous substrates that infect are on the exterior or perhaps even on the interior, these proteins that are involved in infection. And it's just the big problem with proteins, of course, is they make for wonderful drug targets and drug molecules, but they fall apart. So in their native state, they undergo stress and then they fall apart. And you see I've drawn them from nicely folded into some linearized nonsense right here. And that, in essence, is what we are trying to prevent. So how can we prevent the unfolding and denaturation of a native state protein in a way that preserves and enhances a drug therapeutic? And there are ways in which we can approach that, and that is through immobilizing it. Essentially, can we take that native state or wrap it into a straitjacket to keep it from unfolding, and in that way prolong its shelf life? Because proteinaceous drugs have a limited shelf life. Insulin, for instance, has to be refrigerated essentially all the time, and in contemporary days, I'm sure you've heard reports of Moderna and Pfizer's COVID vaccines requiring just incredibly low temperatures, -80, -20, um, in order to be stabilized. That's not so much a protein issue, but it's the same sort of issue. It's a thermodynamic issue. There is a myriad of lower energy, less desirable states that proteins and liposomes and all these things can transform into with just ambient energy, and we want to prevent that. So one way to do that is through confinement with polymer chains. And in a way that we're approaching is we're looking at crystalline materials. So crystalline polymeric systems is an approach that has been looked at before and using this biomimetic growth of phosphate or metal phosphates. But um, we're particularly interested in a class of material called metal organic frameworks, and I'm going to explain what those are. Essentially, those are porous coordination polymers, and through some nice chemistry, we can tune a lot of different properties there. All right. Now, this process, this problem of unfolding, has a number of issues that really come down to something called the cold chain, and the cold chain is this picture right here. It's a logistical network that starts off as a manufacturer, and you end up in a van that gets transported to the airport, and all of these different steps have to be refrigerated. So you can see how a company like Pfizer or Moderna are concerned that, especially in the larger or further you are from reliable power and good infrastructure, the less likely you're going to end up with an intact vaccine by the time it gets there. This whole infrastructure chain, once you have a breakdown, results obviously in a loss of shipment for the rest of the way. And this can add as much as 80% of the total cost of the vaccine, all within this, within just the shipping and insulation and electricity to get something there. And what we are proposing, and what we found actually is fairly effective, is to grow these metal coordination polymers onto the surface of the protein. And these metal coordination polymers that we use are from a class of material called metal organic frameworks. And you can see the rough idea. You've got some sort of metal cluster or a metal ion, and they're connected by small organic ligands. And they coordinate to each other, so it's called a coordination polymer, where a metal coordinates to a ligand to a metal, and they tend to be very crystalline. They are low density, so they're mostly filled with holes. They're free space largely, so they're a very low density polymer. And historically, they're used for gas storage and separation and catalysis and all kinds of other things in industry. And we have found this particular coordination polymer, which actually is methylimidazole zinc, and this orange ball is actually representing empty space on the inside, and it's made out of just these two compounds, this atom right here, zinc, which coordinates infinitely with these two nitrogens, with this imidazole. It's a methylimidazole ring, and so as a consequence, you get this interlinking system that the geometry sort of forces large holes in it, and so you can actually encase a lot of material, a lot of proteinaceous material in a very small amount of polymer in this way. Okay, and it's water stable, stable. It got on two lines right there, and they have these porosities, like I said, and one of the first things we did was we demonstrated that we were able to grow it biomimetically on a virus called the tobacco mosaic virus. And this is a 300 nanometer long viral rod. And just by mixing these two components together, the methylimidazole and the zinc, they self-assemble on the outside of the rod. And you can see in this TEM micrograph, you can see the much lighter virus on the inside, surrounded by the heavier, dense, and more dense, I say more electronically dense because zinc is a much bigger atom, so it has higher contrast by TEM, and the organics on the inside. Now, the shell is actually labile, so this is a remarkably stable material, but it's labile and it falls apart, dissolves very neatly with a chelator like EDTA, or in solutions that are below 7, and you get the virus back. So you can start off with something that looks like this, like little noodles, with a very thin shell. It's 100 nanometers, and a pair of arrows will pop out to show you more clearly. You start with this, and then you throw in some EDTA, and you end up getting the virus back, what we call, exfoliated. All right, we call it exfoliation. So the shell comes off, and you get pristine virus back, and I'll define pristine in a minute. Okay, and we've also looked at how this shell falls apart in things like cell media and serum. Essentially, if you give it enough time, it starts poking holes into it, and if you have a protein inside of here, that protein actually starts to come out. So this is EDTA, so this is a solution. Basically what we did is take green fluorescent protein and grew actually a large crystal with a bunch of green fluorescent proteins on the inside. So there are hundreds of GFPs, tens to 100s of GFPs inside each one of these crystals. And as serum, all right, comes in and starts chewing it up, you can see there is a release of the green fluorescent protein that starts at an hour to 4 hours and 24 hours. And of course, EDTA does it much faster because EDTA is very specific and a good chelator. And essentially what it does, and serum does this too, is it comes in and grabs the zinc out and pulls it out. And that causes the entire polymer just to fall right apart. The reason serum is actually very good at this is because serum is a major part of zinc trafficking in your body, and so it helps maintain zinc homeostasis. So it has actually pretty decent affinity for zinc, and it can induce it to fall apart. But what you'll notice is it doesn't fall apart in water over 24 hours. In fact, it doesn't fall apart in water over the course of years. And the protein on the inside is actually very stable, which is where I get this thermodynamically stable. It effectively is bulletproof to heat and solvent and that sort of stuff, but it's kinetically labile around things that are in your body that can slowly take it apart. And what I mean by stable, how is a protein stable, is so this is a circular dichroism spectrum of the tobacco mosaic virus coat protein monomers. And you can see the natively folded system has a very nice arc that basically corresponds to alpha helices. And then the denatured one isn't a flat line. It still has secondary structure. So denaturation doesn't mean that you're going to a totally unfolded strand of protein. It just means that you're changing the protein's shape. And that in surface science, of course, is very difficult to manage, to view. But in biology, we can just look at how antibodies, antigen-specific antibodies, bind to the surface of TMV. And so if we do that, if we look at use an ELISA response, so essentially an antibodies test, to look at how the surface of the virus changes from just regular virus, so this is our positive control, it has a 100% response rate, and just putting it in the ZIF and then taking the ZIF off, you can see it's pretty much within the margin of error. There's really no difference. The ZIF itself, the growth and the shedding or the exfoliation, doesn't impact the surface. But on the other hand, when we heat it, we see that there is a significant change in how antibodies interact. In fact, the anti-TMV antibodies don't interact very well with the surface at all. That contrasts when it was encapsulated. So in other words, inside of the TMV, those coat proteins in the entire assembled virus can't move. They can't fall apart, and so they can't change shape. They've been locked into a straitjacket, which means that when we take the coat protein off at ambient temperature, we can still bind antibodies just fine. Whereas the regular TMV, that has essentially been cooked. It's pretty much gone. And we've tested it with a number of different stressors as well. Guanidine HCl, for instance, the porosity and the acidity of guanidine HCl has degraded it a little bit because it does that particular stuff attacks the ZIF shell a little bit, but you can still see it's pretty well folded, still about 75% versus absolutely unfolded in the unprotected form. And then common organic solvents like methanol and ethyl acetate. Methanol, of course, is known to as a fixative, so it denatures proteins very well. Ethyl acetate is our typical organic solvent, and dichloromethane is used in some polymer preparations. And so dichloromethane isn't particularly deleterious to proteins in short exposure anyway, but we see very good protection of a protein inside of the ZIF. We wanted to then look at how these did in vivo. So if we implanted the TMV, do we get an antibody response? And again, we can look at that with ELISA. And we also wanted to just see what kind of antibody response we get. What is the magnitude? And what we did was we labeled the tobacco mosaic virus with an organic dye. And that allows us to see it through the skin of a mouse. And did a subcutaneous injection of it into the thigh, which is how you would normally get a vaccine, actually, is just in the skin. Sometimes you get it intramuscularly, which you probably did, hopefully, for your flu vaccine, but it can be into the skin, or a number of different ways, actually. But what we see is that there's a slow dissipation of the fluorescence over the course of 2 days, which is good because that gives your immune system time to acclimate and change and process antibodies or develop more of a cell response against the invading pathogen. What we see in the case of the ZIF-encoded TMV, which I've called TZ-thick here, is that you have a substantially longer residence time of the TMV in the skin. In fact, if we chart it out, we can see that uh, the fluorescence is pretty obvious all the way up through almost 300 hours. So you can see this easily for almost 2 weeks inside of the skin. And so that long residence time has some definitive effects on the immunity that you get out of the TMV. And in our early assessment of what we wanted to look at, we were really only interested in two things. We were interested in seeing how does this affect the tissue, and we basically did some rookie histology, and we saw no changes at all in any of the tissues of the major organs, or even actually in the injection site at the skin. After 40 days, we noticed no difference in the skin. The injection site had completely healed, and it looked really good. And we did some very basic antibodies quantification, and we saw that TMV by itself could produce, actually the TMV ZIF at day 35 started to produce stronger so more anti-TMV antibodies were being produced by day 35, and we declared victory on this and said that essentially the ZIF coding does not alter the antigenicity of TMV. But if we had stuck it out a little longer, what we would have noticed is that by day 90, the humoral response, the antibody response, the total IgG production of the TMV at ZIF is substantially higher. So we're far and above higher than the antibody response of the tobacco mosaic virus. And this was actually pretty interesting. So we wanted to know, then test this out on something a bit more relevant. And then we also wanted to know if this ZIF-8 encapsulation method was more generalizable. So infection by tobacco mosaic virus is not significantly a problem for people. That's not going to be something that happens. But infection by E. coli, that's a tougher nut to crack. There are actually no approved vaccines for E. coli infection. And there are some pretty good reasons for that. We are interested, of course, in using our ZIF implementation to solve a problem with formulating whole cell bacterial vaccines. And essentially whole cell formulations, as opposed to some other vaccine formulations that other people have tried, actually have some benefits. Normal vaccine formulation for E. coli and other bacteria have looked at toxoids, but if you have a bacteria that doesn't produce well-known toxins, you have to look at some of the antigens that are on the surface of the bacteria. And subunit vaccines, so essentially going and trying to find conserved proteins on the surface and then bioconjugating them to a carrier protein, is one strategy, and that hasn't been successful so far. And one of the reasons is thought to be that you have so many different kinds of E. coli, and they have so many different kinds of antigens. Why not just bring the whole cell in? Why not just take the cell, the bacteria, kill it, and then use that as the antigen, right? The other approach is attenuated bacteria, so essentially take a pathogenic bacteria and evolve it so it's not pathogenic. But you would again have to do that for every strain that you want to create an immunity against. And in an infection like urinary tract infection, which is what we're particularly interested in, you can have an incredibly diverse phyology of bacteria, which means you're going to be doing this for a lot of subunits and a lot of different bacteria. Again, possible and a great strategy, but so far it has not brought much to the clinic. On the other hand, whole cell formulations actually have. They've gotten through the clinic, although none of them have been approved for use in the United States. And the problem largely with whole cell formulations or inactivated formulations is that the inactivation process destroys the surface. So in order to ensure bacteria are dead, you have two principal ways of doing this. You can thermally inactivate them, which uses heat, or you can inactivate them through chemical methods. And thermal inactivation is the same thing that causes eggs to fry, and inactivation by chemicals usually involves formalin cross-linking, and formalin cross-linking does actual chemistry to the proteins to either cross-link them or create specific bridges in between two things. It essentially changes chemically the surface. And both of these are pretty well known to degrade the quality and quantity of an immune response that comes out of the vaccines that they formulate. Other things, of course, you cannot guarantee full inactivation with antibiotics, and there are other approaches to activation that are also promising. But at the end of the day, you need a dead bacteria. All of the bacteria need to be dead. All right. Now, Uropathogenic E. coli is actually one of a pretty big problem. It's one of the largest issues in hospitals. So a catheter transmitted E. coli, and it has an amazing amount of precedence. About 50% of all women will develop a urinary tract infection from E. coli. And a lot of these can progress and they become recurrent. In other words, they'll come back again and again. This has a very high level of antibiotic resistance, so UTI can be extraordinarily difficult to treat, and it can progress into septic shock. If the bacteria ascend into the kidneys, it can cause death, and about 200,000 people died of this in 2015. And as you can imagine, that number is set to increase as bacteria antibiotics become less and less effective against these infections. 30% of everybody who has them is likely to get them again, particularly in women, and antibiotics are basically the only treatment. Subunit vaccines have largely been in the development pipeline, looking at specific proteins. They haven't been clinically translated yet, and there are some whole cell vaccines that also have shown more promise, I would argue. Again, they haven't quite made it into the clinic. We applied our methodology to show that we can grow ZIF on the surface of E. coli. And surprising to us, because we weren't microbiologists, we discovered that our process absolutely kills every single bacteria. And that is, we have comparable killing to formalin and just heating the bacteria to 80 degrees. We get no regrowth even after 72 hours of plating. So these aren't just inactivated, they're genuinely dead. Come to find out that zinc is actually a really great binder, and it displaces a lot of different metals in bacterial transporters, and so zinc is an incredible antibiotic, as it turns out. In fact, your macrophages destroy enveloped infections with zinc traps that just pumps them full of zinc and copper and kills them. So nature's own death by nature, I guess. So that was pretty interesting and fortuitous, but we were also curious because we saw that wonderful immune response in the tobacco mosaic virus. Essentially, it was created from a depot effect, so this slow releasing process. We wondered if maybe we could get a two-punch. We can inactivate the surface without altering the proteins, and also perhaps create a slow-releasing depot that enhances the humoral response, those antibodies. And for the chemistry lovers and some of us, what we see is that this shell formation takes about an hour to form. We can actually change the thickness and the variety of shell of our crystals on the surface, so we can scale, make them thinner, make them thicker. And basically that's just our way of controlling how fast or how slowly these come out, and they're released in vivo. And also Yeah, basically we can control the rate by controlling the amount or the thickness of the shell growth. So we conducted a preliminary study, and specifically we actually used a bacteria that's known to induce sepsis. It's a uroseptic bacteria. So this is essentially fatal if you get this sort of bacteria. It spreads throughout your body, and it kills you. And we created two different formulations, an inactivated, so traditional formalin inactivation, the CFT073, which we injected again subcutaneously and very quickly is cleared out. And our formulation of inactivated CFT as if, which goes in and is much remains for a significantly longer time. And we followed this vaccination schedule: one injection, an initial injection, and then two boosters on day 7 and 14. And then we did some blood draws, did some histology, and found no obvious difference in the organs in the tissue or in the skin following injection, as we had discovered previously. 14 days in, we checked the IL-6 levels, and IL-6 was considerably elevated, which was good, although IL-6 goes up if you poke the animal. So the higher IL-6 made us think that we were probably going to see a pretty good response at day 21. And we did. In fact, at day 21, we saw significantly. So this is the day 21 of the CFT at ZIF formulation, and these are the endpoint IgG titers. So it's important I should mention that urinary tract infection is pretty well thought to be tied to how well can you formulate an antibody response. So antibodies go in and then they neutralize the bacteria, and then you urinate them out. The bladder is not great at. The bladder is a funny organ. It does not promote good, strong memory, but what we see is that if you encase the bacteria inside of the shell, you get pretty good anti-CFT titers. At day 42, what we see is an incredible increase. So again, what we're seeing is this really strong, prolonged increase in IgG that you don't see. Maybe you see relative scaling. Maybe I don't think so. These two are barely significant. And certainly with a heat inactivated, those two are not significant. But in the CFT at ZIF, there's a substantial difference. And on rechallenge, what we see in isolated splenocytes are obvious upregulation of IF and gamma. And so we know that there is maturation of T cells in this. And what we really were impressed by, or what we're really happy with, is when we challenged the mice with an infection of CFT073 through a peritoneal injection, most of the mice died, and I'll show you the survival curves in a second. And the mice that died were the saline mice, obviously. So this is the bacterial load and colony-forming units in the spleen, in the liver, and in the heart, all right? And if I show you the survival curves, what we see is that our CFT at ZIF mice had one mouse died, and you can guess which one that was. But those mice survived well past 48 hours. They survived to the end of our experiment, and they were sacrificed so that we could obtain the bacterial load data. The saline, heat, and fixed all survived. We had one fixed mouse that lived, and you can tell which one that is. And then none of the heat and none of the saline mice survived. And the enormous difference in bacterial load in the vital organs and in the blood essentially paint how that happened. You just didn't really get a significant infection, a reinfection following challenge. In some animals, in fact, we didn't observe any colony forming units at all. This is the lower limit of detection. And this is pretty impressive. We followed essentially a published protocol on subunit vaccines, and the CFU counts in the organs, you saw some increase in survivability from subunits, but you did not see actual elimination of bacteria in the mouse after challenge. So that was really quite impressive, and we were quite happy with that. Of course, as you probably guessed, I didn't do any of this. I have a charming and wonderful team of trainees that work hard. This work, really, I have to give most of the credit. I should give, in fact, I'll just give him all the credit because what difference does it make? It was Michael. He's graduating now. He's heading off to Harvard Medical School to do a postdoc. Fabian was a big help here too. Fabian is a third year. He's also just incredible. And then the entire team, of course, helps. And I'm happy to now answer any questions.